Modular arithmetic is an aspect of mathematics that. Hello, dear students. I welcome you all to today's mathematics class. My name still remains Mr. Moses S. Babatunde. Actually, we have quite a number of topics we're going to consider today because we are revising both WAEC and NECO past questions. So the first topic on the past question is approximation and estimation. What is approximation? Approximation is an aspect of mathematics that deals with representing figure in a precise and concise form following a given format. There are several formats we can be given in an exam. One is decimal place. We can be asked to represent or approximate a given figure into a decimal place. 2. Significant figure. 3. Nearest 10. 4. Nearest 100. 5. Nearest 1000. And 6. Nearest whole number. Let us look at what the first question we are considering now. Let's look at the question. Let's see what it says. 1. It says evaluate correct to two decimal places 62.7504 minus 25.78 plus 5.63. And here are the options. How do we go about solving this type of problem? Let's see what to do here. We're going to write the first figure we are given. 62.7504, then minus 25.78. So we have subtraction here. We're now going to draw a line. We are going to have a line. Put a figure here. Put a figure here to fill the gap. So if we want to solve this problem, we are going to say 4 minus 0, it gives us 4. 0 minus 0, it gives us 0. 5 minus 8, impossible. We are going to borrow 1 from here and put here, it becomes 15. 15 minus 8, it gives us 7. Then this one remains 6. 7 from 6 is not possible. We are going to borrow 1 from here and add to this one. This is 16. 16 minus 7, it gives us 9. Then this one remains 1. Removing 5 from 1 is not possible. We are going to borrow 1 from here, put to this place. That is 11. 11 minus 5, that gives us 6. So here remains 5. 5 minus 2, it gives us 3. Then we are going to look at the next one, which is 5.63. We are to add 5.63 to that figure. 5.63. See the pattern of the arrangement. You must make sure that the decimal points follow each other. The decimal points must follow each other. So here is this. We are to add this one. If you want to add, you are going to fill all these other places too. Fill all these other places. 4 plus 0, we have 4. 0 plus 0, we have 0. 7 plus 3, that is 10. We are going to write 0, we keep 1. Then that one we keep. 9 plus 6, it will give us 15. 15 plus 1, that we keep, it gives us 16. Here is, we write 6 and we keep 1. 6 plus 5, it gives us 11. 11 plus 1, that gives us 2. So the decimal point is still in order. So here is 2, we'll keep 1. 3 plus 0, that is, it gives us 3. Plus 1, that is 4. So this figure that is here, we are to approximate correct to the nearest two decimal place. What do? We are going to start the counting from the decimal point, and then we'll proceed to the right hand side. If we move now, 1, 2, we are going to stop at this point. So the next number, the next digit here is not up to 5. So because of that, we are going to throw it away. So the available figure now, which is the appropriate one, is 42.60. And when we look at the option, it is option A that is correct. I want to believe it's very clear. Now, the next question, as specified by WAEC and NECO past question of this year, is set theory. What is set? Set is an aspect of mathematics that deals with arranging figure or objects according to a given pattern. It comprises of the universal set and the subset. The universal set is the mother set, while the subset are the children. Now let us look at that question of that year. We are told that if A, being a subset, is equal to x such that x is less than 5, that means that we are going to look for numbers that are less than 5, excluding 5 itself, and subset B, which is equal to y, such that y is a factor of 18. So under subset B, we are going to look for numbers that are factors of 18. And the universal set begins from 1, 2, 3, it ends at 10. That means all the figure we are going to obtain for subset A and subset B, they must not go beyond the universal set, because that is the mother. There is no how a child will grow wing more than the capacity of the mother. So it has to be within the ability of the mother. Now we are now asked to find A intersection B. The meaning of A intersection B is that elements or set of elements in A that can also be found among the set of elements in B. So those sets of elements, we are going to bring them as the answer, and that is going to be the answer we are looking for. Now let us quickly look at how we are going to solve the problem. First and foremost, subset A. Numbers that are less than 5, excluding 5 itself, they are 1, 2, 3, 4, excluding 5 itself. So when we have x less than 5, that is to say excluding 5, so we have to look for figures that are less than 5, excluding 5 itself. So here are those figures, and it has to be within the context of the universal set. The universal set begins from 1, 2, 3 up to 10. So we cannot go beyond the universal set. Otherwise, we could have extended it up to 0, -1, -2, -3, and so on and so forth. But because of the specification given to us by the universal set, we have to limit the figure of subset A to 1, 2, 3, and 4. Now let us come to subset B. Subset B is equal to factor of 18. How do we get factor of 18? We are going to put it this way. We have 18 this way. 2 goes in 18. We have 9. Can 2 goes in 9? No. What about 3? Yes, 3 can go. 3 goes in 9. We have 3. What else can go? 3 can still go. 3 go in 3. 1. So the subset B, the figure which we can refer to as the factor of 18, they are 1, 2, 3, 9, and 18. We could have included 18, but because this universal set says 1 to 10, so that 18 is cut off by the universal set. So we're going to limit the figure to this. These are subset B. So the question says find A intersection B. Like I said, intersection means numbers of figures that are common in between the two subsets that we are considering. So we are considering subset A and subset B. What are numbers that are common in between subset A and subset B? The first number, which is A intersection B, they include 1 is common, we are going to write 1. 2 is common, we are going to write 2. 3 is common, we are going to write 3. Is there any number that is still common? There is no any other number. And so this is going to be the final answer. Let's look at the correct option. Option A, wrong. Option B is correct. That is the most appropriate option. Option B is the most appropriate. I want to believe it's very clear. In question 3, as specified by WAEC and NECO past question of this year, the question says simplify square root open brackets 16 all over 9 close bracket raised to power 3 over 2 times 16 raised to power minus 3 over 2 close the bracket. Then there is 1 over 3. This question centers majorly on indices. What is indices? Indices is an aspect of mathematics that deals with simplification of terms with respect to their index or power. So the plural form of index is indices. And there are various laws that govern solving problem in indices. We have the multiplication law, the division law, the unit power law, the zero power law, and we also have the fractional negative power law. So the law that is applicable that we are going to use to solve this particular problem is fractional negative power law. Let us see how we are going to apply the law in solving this problem. Here is simplify 16 over 9. We are going to adopt the principle called knockout principle. First and foremost, we knock out this negative. How do you knock out this negative here? You are going to have 9. That is, we have 9 all over 16. All over 16. What I've just done here is to ensure that denominator become numerator and numerator become denominator. By so doing, I knock out negative sign from here. So once I do like this, negative sign has been knocked out. So I'm left with 3 all over 2. Then times 16 all over 1. There is 1 here, invisible 1. 16 all over 1. So if I want to knock out this negative sign, numerator, which is 16, will become denominator, and denominator, which is 1, will become numerator. That is to say, I'm going to have 1 all over 16, and by so doing, minus has been knocked off, so I'm left with 3 all over 4. So we have a bigger bracket here and here before you now have 1 over 3. We are at knockout stage. How do we knock out 2? Because already we have knocked out all the negative signs that are represented. The next thing is for us to knock out 2. How can we knock out 2 from this concept? We are going to have what we call this. 9 over 16 can be changed to 3 all over 4 raised to power of 2. 9 is the same thing as 3 raised to power 2. 16 is the same thing as 4 raised to power 2. So this 2 here, this power of 2 here affects both the 3 and 4. And it is this power that makes this one to become 9 all over 16. So we can now introduce one bracket here. This is going to be 3 all over 2. The 3 all over 2 that was there before is now here. Knocking out stage. This 2 here that is obtained from 9 over 16 to be 3 over 4 all square. These 2 can knock out this one. We are at knocking out stage. Then again, let's proceed. Here is 1 over 16. 4 or 2 raised to power 4 can be obtained from 16. That is to say, we are going to have 1 all over 2 raised to power 4 altogether raised to power 4. 1 over 16 is the same thing as 1 over 2 raised to power of 4. So, here we are going to have this 3 over 4 is now there. 3 over 4 is here. Knocking out stage. This 4 that is obtained from 1 over 16 that make it to become 1 over 2 can be used to knock out this 4. This one cancel this. So we are at knocking out stage. We are now left with this 3 here and this 3 here. This is 1 all over 3. The final 1 over 3. So if we proceed from here to this point, we have 3 all over 4 raised to power of 3. 2 has been knocked out. 4 has been knocked out. Then we have 1 all over 2 raised to power of 3. 4 has been knocked out. So we have something like this, 1 all over 3. Eventually, there is power of 3 here, there is equally power of 3 here. The multiplication law says that when we have power of 3, when you have two different terms that are having power, equal power, the same power, you can represent them in this way, which that means we are going to have 3 all over 4 multiplied by 1 all over 2. Since the two of them are having the same power of 3, we can represent them this way. Look at it. This one is having power of 3. This one is also having power of 3. We can connect them together because they have the same power. So we are going to now have 3 over 4 times 1 over 2 altogether power of 3. Then we have the final 1 over 3 here. This 3 that is here can knock out this one. And then we have this knocking out stage. In the final analysis, we are going to have 3 all over 4 times 1 all over 2. And that will give us 3 all over 8. 3 all over 8. We are going to have 3 all over 8. So the final answer is going to be 3 all over 8. I want to believe it's clear to everybody. That is very good. We are now in number 4, WAEC and NECO past question. And the topic has to do with modular arithmetic. Modular arithmetic. What is modular arithmetic? Modular arithmetic is an aspect of mathematics that deals with counting in bundles and focusing on the remainder. Counting in bundle and focusing on the remainder. The bundle is equivalent to module. Let us take for instance, if I have 34 module 9. That is to say that I am to count 34 in bundle of 9. Then my emphasis is going to be on the remainder. Let us have this. We have 34 is going to be 9. This is the first bundle of 9 plus 9 plus 9. Altogether now, this is 18. This is 27. Then I need to still go further. 18 plus 9 giving me 27. Then plus 9 again. If I add 9 to this one, it will give us 36, which is more than 34. So what I'm going to add to this 9 to give me 34 is 7. And so 34 modulo 9 is going to be the same thing as 7 modulo 4. 7 modulo 9. 34 modulo 9 is a senior brother to 7 modulo 9. The two of them, they are the same, they are equal in value, because the remainder of this 34 as we count in module of 9 is 7. So that remainder is having equal value with the senior brother, which is 34 modulo 9. Now let us look at another one. If I have 25 modulo 9, I want to count 25 in bundle of 9. What I'm going to say, I will start with 9. This is the first bundle, then the second bundle, then this plus this, that is 18. I will now remove 18 from 25. It gives me 7. 7 is the remainder, the leftover after counting in bundle of 9, counting 25 in bundle of 9. That shows that this 7 that is the remainder is the younger brother also to this 25 modulo 9 is having equal value with 7 modulo 9. So 7 modulo 9 is also a younger brother to 25 modulo 9. Now let us look at another one. 16 modulo 9. 16 modulo 9. This 16 modulo 9, if I want to count 16 in bundle of 9, I'm going to say 9 plus, if I add another 9, it will go beyond 16. So what is going to be the leftover? If I remove 9 from 16, I'm going to have 7 modulo 9. That shows that 7 modulo 9 and 16 modulo 9, the two of them are equal in value. So if I watch 7 modulo 9, 16 modulo 9, 25 modulo 9, 34 modulo 9, all of them, they are senior brother to 7 modulo 9, 7 modulo 9, 7 modulo 9. So that means as we have this group, we have the group of 16 modulo 9. This 16 modulo 9 is having equal value with 7 modulo 9. Then 25 modulo 9 is also having equal value with 7 modulo 9. Then 34 modulo 9 is having equal value with 7 modulo 9. The reason is because after counting each of them in bundle of 9, the leftover, which is the remainder, is always 7. So based on that, we say that 16 modulo 9, 25 modulo 9, 34 modulo 9, they are senior brother to 7 modulo 9. Now let us look at how we are going to now answer the question. The question says, find the least value of x which satisfies 5x is equal to 7 modulo 9. As we look at this, we want to find the least value of x. So all that we need to do, we will have just decided to divide both sides by 5. But if we should divide both sides by 5, 5 cannot go directly inside 7. There will be a leftover. So because of that, we will look for another bigger number, another number that is having equal value with 7. So the number that is having equal value with 7 modulo 9, they are 16 modulo 9. So if I replace 7 modulo 9 with 16 modulo 9, it's still the same thing. I've not done anything different. But if I replace it, 5 cannot go inside 16 modulo 9. So let's try further. If I replace 7 modulo 9 with 25 modulo 9, 5 can easily go inside 25. So the most appropriate value that will have the same equivalent with 7 modulo 9 and will be able to divide 5 is 25. So 25 will be the most appropriate value I'm going to use to replace 7 modulo 9. And now let us see what will now happen. I'm going to say solution 5x is going to be equal to 25 modulo 9. I have been able to replace 7 modulo 9 I replace it by 25 modulo 9 since the two of them are the same thing. This one is just a sibling in the family of days. So they belong to the same family. 34 modulo 9 is also part of the family. 16 modulo 9 is also part of the family. But we have to look for one that can perfectly divide 5, and that is why we choose 25 modulo 9. So let us divide both sides by 5. We now have divide both sides by 5. When we divide both sides by 5, we are going to have 5x being equal to 25 modulo 9. And this one will divide by 5, divide by 5. This one will have 5. We'll have 1, 1. So we have final answer is going to be equal to 5. So let's answer now is 5. Let's look at the A, wrong, B, wrong, C, correct. So the most appropriate answer to this question is 5. I want to believe it's very clear to everybody. Now, number 5, as specified by WAEC and NECO past question, is under logarithm. Logarithm without table. This number 5 says express 1 plus 3 log 2 base 10 in the form log x base 10. Express 1 plus 3 log 2 base 10 in the form log x base 10. And here are the options. In logarithm, when we say logarithm, we mean logarithm of a number x to base y is p to which y must be raised to give x. That is to say, logarithm of a number x to base y is p to which y must be raised to give us the value x. So that shows in logarithm, if we are looking for the value of x, this p, y must raise to power of p. That is what the logarithm is saying. And there are quite a number of laws that govern solving problem in logarithm. We have the additional law, we have the multiplicational law, divisional law, subtractional law, and we have equal law. We also have the power law. So out of all those laws that govern solving problem in logarithm, the one that is most applicable here to this question is the equal law and the power law. What does equal law, what does it say? Equal law says that when you have logarithm of a number like 2 having the same base, equal base, the law says that it's going to be equal to 1. The value of this one is going to give us 1. This is equal law in logarithm. Also, when we have logarithm of 5 to base 5, the answer is going to be 1. Also, when we have the logarithm of 10 base 10, the answer is going to be 1. That is the law, one of the law of logarithm, and that is equal law. Now we have another law, which is power law. That power law says if you have a number like 2 raised to power of 3, 2 base 10 raised to power of 3, you are permitted to transfer this power down to this point. That means you are going to have this one now become 3 log 2 base 10. This is one of the law called power law. The power has been transferred. The power can be transferred from one end to another end. So this power, which is 3, the index has been transferred from here to this place. And that is how it becomes this. Now from the question, here we have the equal law and the power law to be applied. Let us see the way we are going to apply. Let's see the way we are going to apply the two concepts, both the equal law and the power law. For us to be able to apply the two of them, looking at that question, we have 1. So if I look at the partner here, this one is having base 10. So I can as well represent 1 to have base 10 with this. This is what will happen. So number 5 can now be expressed as this. The solution to this can now be this 1 plus 3 log 2 base 10. This one can be replaced and represented by log 10 base 10, which is still 1. Then I will apply the concept of power law. That is, these 3 can be transferred back to where it was before, which means I'm going to have something like 2 raised to power 3 base 10. Now, after this, I can proceed to the next law that is called multiplication law. Multiplication law says that when 2 terms are added together, they can be changed to multiplication. Now let us see, this is a 10, this is another 10, they are added together. Since they have the same base, addition law says that this addition can be changed to multiplication. So let us see how we can do that. What we just need to do, since they have the same base, we'll pick up the base that they have. We'll pick up the base. The base is log base 10. This one has the same base with this, so we'll pick up the base. Then, what is left here is 10. Then we now change it to multiplication, because positive can be changed to multiplication. That is the multiplication and addition law. Here is 2 raised to power 3. Now, it has been changed automatically to multiplication, just because this and this, they have the same base. I can now proceed and say this one will now be equal to 10 times 2 raised to power 3 means 2 in 3 places. 2 in 3 places. 2 in 3 places. 2 times 2 times 2, that is 2 raised to power 3, and that gives us 8. This is still base 10. So if I work on this one, 10 times 8, it will give us log 80 base 10. Log 80 base 10. Let us check the option that is most appropriate. So option A is wrong, option B is wrong. The most appropriate option here is option C. I want to believe is very clear. That is very good. But I want to remind us that you should try as much as possible to subscribe into this channel. It is very, very important. Now we have come to the end of today's class.